To solve this example problem, what we do, as ever, is to draw out what's happening. So here I'm going to draw the pan. There is the pan handle in which we are frying this bacon, and here is the surface of the stove range upon which we are frying the bacon. Here's the little bacon that starts slipping as soon as we raise this side of the pan up to a height of 5 centimeters. So let's write that in as well. From here to there, that is 5 centimeters. And then they also tell us the length of the pan from the pivot point, which is going to be, I guess, this point right here where we're pivoting the pan up. From there to where we're measuring the height, that's some length, and it is equal to 23.5 centimeters. Okay, so we've got a pan. It's raised to a height. As we pivot up, it has some length. There's bacon in it. The bacon starts slipping as soon as we get to this height. And what do they want us to find? They want us to find the coefficient of static friction. That's the goal right there. Okay, so how would we do this? Well, they're asking about the coefficient of static friction, which means we're going to have to figure out something about the friction force, which means this is probably a Newton's second law problem. So in that case, we're going to need a free body diagram. We're going to figure out which object do we need the free body diagram for. That would probably be the bacon, because we're asked for the coefficient of static friction between the bacon and the pan. And the bacon's the thing that starts moving after we've hit sort of, I guess, this maximum height we can go. So we're going to want a free body diagram of the bacon. So there is the bacon, and now we need the forces on the bacon. Well, certainly we are probably doing this on Earth, so it'll have gravity. So I'll draw the force of gravity down like that. We're looking for friction, so we know there probably is friction, and in fact we know there must be friction because the bacon isn't moving until we get past this height. So something was keeping the bacon from sliding down the pan. It must have been friction, so friction was opposing the motion, so it is going up the pan. Parallel, of course, to the surface of the pan, because friction is the parallel surface force. And there is, of course, another surface force, and we can tell it's here as well, because the bacon is also not dropping through the bottom of the pan. Something is pushing up on it from the surface of the pan, and that's the normal force, perpendicular to the surface. So the friction force and the normal force are, of course, perpendicular 90 degrees to each other, because the friction force is parallel to the surface, the normal force is perpendicular to the surface, and gravity is off just kind of in its own XY plane. So when it comes to time to choose a coordinate system, we could do our normal vertical and horizontal, but we could also do kind of like parallel to the surface of the plan and perpendicular. And I vote we do that one, because we got two forces that are lined up with that axis system and only one force that's lined up with our normal vertical horizontal. So let's choose perpendicular to the surface and parallel to the surface. Parallel will be our X and perpendicular will be our Y. And now that we have our free body diagram and our axis system, we are set to go use Newton's second law. So the net force, which is a vector, equals the mass times the acceleration, another vector. And we know we can split this up into X and Y component equations. And let's see, let's go ahead and do that. The net force, the X component of the net force, is equal to mass times the X component of the acceleration. And the Y component of the net force is equal to mass times the Y component of the acceleration. And we don't need the vector arrows on top of these guys anymore because we have split it up into components. We've already got encoded in the fact there are two equations. This is a vector. And let's see what else. We're looking for the coefficient of static friction. So that's going to be attached to friction. Friction's in the X direction. So let's see if we can do this problem with just the X direction. So forces we've got in X. Well, certainly the friction force is in X. It's completely in X. No components in Y as we've drawn them. And then gravity is going to have a bit of an X component because of how we've chosen our X and Y. The friction force, that's going up. That's the positive x direction, so up along the pan. So friction force is positive. Gravity, that x component of gravity, that's going to go down, sliding down the surface of the pan, so that'll be negative. And then mass times the acceleration. So I guess since we know we have to divide gravity into components, and we knew that already when we did our free body diagram, let's go ahead and do that. So there's gravity. Go ahead and draw. Let's see, y is perpendicular to the surface of the plan. So that'll be the y component of gravity. X is parallel to the surface of the pan. So x component of gravity will be like that. There's our right angle opposite our hypotenuse, which of course is the magnitude of the full force, as it always should be when we're dividing a force up into its components. The magnitude of the force is always the hypotenuse of that triangle. And now we're in trouble because we've got the magnitude, we have the hypotenuse, but we don't have an angle here. So maybe angle information is hiding somewhere in our original problem. And we can say, oh look, this looks very much like a right triangle. There's the right angle, the length of the pan, I guess, that's opposite the right angle, so that's the hypotenuse. And then theta, we do this as our theta, then we have the opposite side of the right triangle and the hypotenuse of the triangle. So that would be sine of that angle, I guess, would be equal to the opposite side, which is h, over the hypotenuse. So then theta itself, this theta we've drawn, is the arc sine. Got to undo the sine to get the angle by itself. The arc sine of this fraction, h over L. So we've got the angle. Now we just got to figure out which angle here corresponds to what angle on this different triangle. Well, there are a couple of ways you can do it. One is that normally gravity only has a y component. And if we were to lower this pan down, then y, which is the perpendicular direction to the pan surface, would become what gravity is. So the lower the pan gets, the smaller the angle theta, the closer gravity gets to the y direction. So that points in the direction of this guy, that angle on the gravity component triangle being theta. However, if you're less comfortable with that, then let's redraw on our force diagram what's going on. We won't use the bacon color, we'll use a different color. So I'm drawing the x-axis down. The x-axis is the surface of the pan. And if I draw the horizontal direction there, then this is my angle theta. There's a right angle. Horizontal, gravity is always vertical. And then I'm going to extend my y-axis here down. And if this is theta, then this angle here has got to be 90 degrees minus theta. And that's because the interior angles of a triangle have to add up to 180 degrees. So 180 degrees, well, this one's 90. So 180 minus 90 leaves me 90 degrees left to split between these two angles to do up the interior angles of a triangle. So if this is theta of that 90 leftover degrees, this guy's got to be 90 minus theta. And this here, the x and y axes must be 90 degrees as well, perpendicular to each other. So if this is 90 degrees and this is 90 minus theta, then that guy's got to be theta. And that theta is the same as this theta. So two different ways to figure out how to relate the angles in this triangle to the angles in this triangle. You can, of course, also do a whole bunch of stuff where you're looking at, parallel lines and which angles have to be the same there. But however you're comfortable with it, just kind of work the way through, like we can find this angle theta. How do we get it onto a gravity triangle? Once we've done that, now we can divvy up these guys, these components, using the trig functions. So if this angle's theta, and that means the y component of gravity is equal to the magnitude of gravity, Fg, and that's the adjacent side to the angle. So this is cosine of that angle. And this guy is the opposite side of that angle. So that's the hypotenuse, the full magnitude of gravity times the sine of the angle. And then we can also plug in what we know about gravity, that it's equal to mass times the acceleration due to gravity times the cosine of the angle. This guy will also plug in the magnitude of the gravitational force, mg, times the sine of the angle. And we got our components. We're all set to plug them in here. But now we got to figure out, what do we put in for the friction force? Well, we are looking for the coefficient of static friction. We know that as soon as we get to this height, you go any higher, that's the limit. That's when the bacon starts to slip. But the coefficient of static friction, that only shows up when you're at the max static friction force. Then that's equal to the coefficient of static friction times the normal force. So are we at the maximum friction force? Yeah, we are, because as soon as we hit this height, that's when it starts slipping. Before that, we were below. We were at some amount of friction that was less than this. And you can sort of look here and you can say, all right, actually, let's look at the math here. So the x component of friction, that's the piece of friction, or sorry, the x component of gravity, that's the piece of gravity which is opposing the friction force. As this angle gets bigger and bigger, the sine of that angle is also getting bigger and bigger. Because remember, we started with the pan flat down on the surface of the range. So this angle, when that was happening, when the pan was lying on the range, the angle was 0. And then slowly we lifted one edge of the pan up off the range. And so theta was going from 0, getting bigger and bigger. It hasn't gone to 90 yet. It's still sort of being lifted up. So as it's being lifted up and this angle is between 0 and 90 degrees, sine is getting bigger and bigger. So the component of gravity that's sliding down the pan, that gets larger and larger as we increase this angle. That means friction, which is the thing keeping it from sliding, has to get bigger and bigger, has to match the x component of gravity. And so the static friction, which it has when it's not sliding, is getting bigger and bigger and bigger until we hit this height and that angle. Then that's too much. We've hit the maximum amount of static friction we can get. The bacon starts sliding. So yeah, right at this angle, not after, but right at that angle, we're at the maximum value of static friction. So we can go ahead and plug in this for our static friction force. And then gravity, we got that. That's over here. mg sine theta. And at the max static friction, just before the friction breaks, it's not big enough to deal with gravity and the bacon starts sliding. The bacon has been at rest and it's remained at rest, and this is in fact the very last moment that it'll be at rest. So the acceleration then is 0, because the bacon, until we hit this angle, the bacon wasn't sliding, it wasn't moving, and it remained not moving. So the velocity wasn't changing, it was 0, and it stayed 0. So the acceleration was 0, and that makes this whole side 0, because anything multiplied by 0 is 0. Okay, what's our goal? Our goal is to find the static coefficient of friction. So let's move all of this stuff over to the other side of the equation. So the coefficient of static friction times the normal force is equal to the mass of the bacon times gravity times sine of the angle. And again, we're solving for the static coefficient of friction, so it's multiplying by the normal force. So we'll divide both sides of the equation by the normal force. There we go. Okay. Do we now know enough to solve for the coefficient of static friction? G we know. Sine of theta, well, we've figured out theta. We know h and L, so we can get a number for theta, so we can plug that into sine, so that's good. We don't know the mass, though. That could be a problem. We also don't know the normal force, so we're not quite ready to solve for the coefficient of friction. Well, I don't know what to do about the mass, but the normal force, it's going to show up in the y component. So let's start with the y component here. And we'll just draw a little line here so you don't mess up our x and y. Remember, once you go to y, ignore everything you know about x. Just solve with the y stuff. All right, what are the y forces? The normal forces in y. So write that down. And the y component of gravity is, of course, in y. And then we got the mass times the y acceleration. Who's positive? Who's negative? Normal force. That's putting up off the pan. That guy's positive. Gravity. The y component of gravity is down. Down and down like that. So that's negative. What else do we know? Well, the normal force, we are solving for that. So it's okay that we don't know anything about that. Y component of gravity. Oh, here it is. So we'll sub that in. Mass times the acceleration due to gravity times the cosine of the angle that we solve for with that, equals mass times acceleration. What do we know about acceleration? Well, the bacon does not suddenly start levitating off the pan or burrowing into the pan. As far as the y direction is concerned, it is at rest in y and it remains at rest in y. So the acceleration in y is 0, which means this whole side of the equation is 0, which means we can solve for the normal force. And here I have just added mg cosine theta to both sides of the equation, and we can go ahead and plug that in right there. But because we're running out of room, let's do it over here instead. Coefficient of static friction equals mass times gravity times sine of theta. I am just copying all of that over here, and then I'm going to sub in normal forcey stuff. So the normal force is equal to the mass times gravity times the cosine of theta. Oh, how nice that is. Look, we've got mass and mass. So we're multiplying by the mass and we're dividing by the mass, and that means the mass cancels out, which is great because we have no mass. And we're also doing the same thing with gravity. We're multiplying by gravity and we divide by gravity, so it cancels out. Then we're left with sine of the angle over cosine of the angle, and sine of an angle over cosine of that same angle is tangent of the angle. So mu s is tangent. Now let's plug in what we know about the angle. So we'll do big square brackets here. Tangent of arc sine of h over L. And now we are finally ready to plug things in. We know h, we know L. That was what we started the problem with. So tangent of arc sine of h, which is 5 centimeters, over L, which is 23.5 centimeters. And we have centimeters over centimeters. Those units will cancel out. How nice. Because for the arc sine, just like for arc any trig function, you can't have units inside the argument. It's got to be unitless, or something has gone wrong. So tangent of arc sine 5 over 23.5. Get at our calculator. That is 0.213 and other stuff, but we'll cut it off there. And then tangent of, let's evaluate the arc sine of this guy. That is 12.8 degrees and other stuff, but it's in degrees because I have my calculator in degrees. And then tangent of that angle in degrees is 0.21775 and other things. And now we do sig figs. We were doing multiplication here, so that means we just go with the number of significant figures rather than the decimal place. Well, multiplication, division, they're the same thing as far as sig figs are concerned. So we had 5, that has 1 sig fig, and 23.5, that's got 3. So the 1 sig fig is the fewer, that's the one we go with. So this is equal to 0.2. There's our answer. And when we check it in the back of the book, we agree with them.